Thank you. Good afternoon, everyone. Yeah, it's a bit optimistic now to say that we'll be generating code right now from the natural language, but that's something that we are trying to get to. Yeah, so my name is Misha, and I'm a physicist by training. I basically spent all my career in academia trying to build the models that would explain us how the complex system really evolved from hydrodynamic to atmospheric dynamics and like neurobiology. So I'm not a developer, and what you will hear about the code right now is basically my adventure and what I really have seen in code and the intelligence we were able to get, but just from analyzing it using different mathematical models. And I hope it will be interesting for you. So let me start with this question. I think if not everyone is a software engineer here, at least everyone codes, right? Who didn't write the single line of code in this auditorium? Is this such a person? No, there are no such people. Okay, so this question should be valid for you. So how much time do you think software engineers code? Who thinks more than 50% of their time? So you all think that it's less than 50%? Okay, so actually you are very right, and amazingly, software engineers spend about 5 to 28%. So there were two studies very recently, one from Microsoft Research that said that software engineers spend for authoring and co-authoring about 28% of their time. A bit more detailed study from SMU here in Singapore showed that only 5% software engineers spend on coding. The rest, they either just communicate to each other or they try to understand what's actually has been written before. So which is like about 60% of the time. So like since pretty much every one of you probably familiar with the Brooks law, you understand how fast the complexity of interactions grow actually when the team is growing. So when you're just 3 developers in a startup, it's super simple to explain what's actually going on. Once you are working in a team where there are 20 people, 50 people, and so on, it's extremely difficult. And in meetings, understanding what has been written before actually eats up pretty much all of the time. So imagine that how wonderful it would be actually if all these problems, such an unsustainable system, would be solved if we would have all the patterns in our mind and how all the different ways and how the problems could be solved and how it has been solved already in different ways. Basically having a GitHub in your mind. Well, not the whole GitHub, only good part of it. Obviously, we will think that something like this would be able with the application of AI, because we live in such an era where already images and video processing and Siri and Alexa, driverless cars and unbeatable AlphaGo completely change our perception of the world, really. So where we are right now in terms of understanding what's actually going on in code. So because sometimes reality and perception is slightly different. Well, we are now building blocks actually that will allow us to get these treasures out of the data to this code. And what are these building blocks? Well, very recent research on few of those showed that we can get absolutely amazing results. So there's been done some work on code completion, where people basically looked at the structure of the code, analyzed it topologically, and using a deep learning and other machine learning methods, then build the models that were able to complete code, especially if everything is named properly, which is very seldomly the case, but still it works sometimes. Code optimization, well, basically imagine that you write a code and you don't care whether it's optimized for CPU usage or even if it's like readable by others. So there are models that help you to optimize the code so that it's taking less space, less memory, and so on and so on. Automated code review. Well, this is something that quite a lot of people spend quite a lot of time, and intelligent code reviews using deep learning is something that is very interesting. Basically, when the model look at all the code reviews that happen in the past and recommends how the code review should happen for your particular project. Bug detection and automated bug fixing, I suppose, is probably a holy grail of software engineering projects. It would be great to solve it. So right now, our research is at the stage where we can help with the bug fixes based on like in name-based models, basically. So we can take a look at how you name the variables and functions, and based on that, help you to detect bugs and even sometimes fix the bugs. So I did improve one of these models actually a bit, and in 8% of the cases, it was fixing the bugs with the accuracy of more than 80%. So it's very good, but in very, very small test cases, but very promising too. And finally, documentation generation. So according to GitHub studies, most of the people, they hate writing documentation. When they even finally did write it, they hate updating it even more. So this is something, the number one complaint. And it's not just that, actually. So let me ask you a question. So what do you think is the result of this run? Would it be true or false? Who thinks it will be true? Everyone think it will be false? Who think it will be false? Okay, so this is false. Okay, what about this one? What do you think? Do you think it will be true? Who thinks it will be true? Who think it will be false? Okay, this is true. So basically, for me as a physicist, this is absolutely mind-blowing. And without documentation, and this is a simple example of how bizarre could JavaScript be, and that's why we are writing usually in academia in C or Python at worst. So, but this is like the simplest one. Imagine like what kind of code disasters or monsters could be inside then without proper documentation. Very difficult actually to crack it. So that's why, and especially for me, the code documentation is at best when it's a Stack Overflow operation. So I ask a question and I got the answer, and with the labels I can explore a bit further. So now, in order to get really to the translation of code, or in particular, I will be talking more about the auto-generated documentation, we should first ask what is really code. So code can be seen at very different granularity levels. It could be seen as a sequence of bytes, sequence of characters, sequence of tokens, or as a tree. So as you can see, this structure actually is very similar to text. Text also could be represented pretty much all of these forms, except for a tree. Some may argue that tree also could be a representation of text. That's why it's very natural to approach the problem of analysis of code from an NLP perspective and just treat code as text. There's been quite a lot of studies on that just took this approach, but they all show that this is a tremendous oversimplification. You actually can do that, but you will not get much out of the code in this case. One of the simplest reasons is because, well, the regularity already is defined in language, and when you will be treating language, a programming language, just as text, you will be relearning it again and just waste a lot of GPU time and money and everything. At the same time, there is a language syntax and language semantics, which are very different actually in natural languages and code. There are some trade-offs, but that's pretty much the same difference. So you can see it even better on this wonderful graph. As you can see, my hand was not very hard when I was drawing it, but you get the meaning. So we see here learning effort, basically on how much training time and data you have to invest in your models that will be capturing the semantics of the code, basically trying to understand what's actually going on, against analysis effort, which is a semantic depth, how much you will actually understand about it. So here on the left side, you can see token string, which basically means that you are treating code as text. So you just have a string of tokens and you analyze them. Then we have a tree representation, which is AST. It stands for abstract syntax tree. It's tree representation of code, which you can analyze topologically. They have semantic and semantic analysis dependency graph. So basically, the further you go to the right, the more language-specific and task-specific your model is becoming. So you are really getting a very good answers and a very precise ones, but and you actually don't spend that much time on training, but you cannot use it for anything else. You're just answering one isolated question. The opposite of that, if you just treat code as text, you are very language agnostic because you don't care actually even about the regularities of code. But then it takes you a lot of time to train any model, and you're also losing a lot of stuff. So in order to get to to represent the code, you probably should work somewhere here in the middle, in the golden middle, which is basically located around the topological structure of code, which is usually ASTs, abstract syntax trees, and go a bit further up here and a bit down here. It depends, always depends on the task. So this graph is probably one of the key problems. It represents one of the key problems that people are coming back again and again. And the question is on how should you represent the code really? Because in NLP, you know that there is a term of notion of word embeddings. And word embeddings, they work with words. So what should be an analog here? Should we work on the token level or on the tree level or even on a bigger level? And this question, I think there is no silver bullet. I'll show you a couple of approaches that we did take. So the first approach that we did in order to generate automatically generate documentation was an unsupervised model, which was treating code as a number of tree paths. So basically imagine that you have a tree that represents your code, and then you go through this tree from one leaf to another one. And then as a collection of these trees, you just represent it as a continuous multidimensional vectors, and then you feed them into the model in order to capture the semantics of what actually is going on inside. We use the very classic libraries and build our models on top of them. As an architecture, I use the tree-based LSTM. So basically the version of LSTM that fits very well to the tree representation of code. In this sense, it's very intuitive to use it, and syntax-aware tokenization to optimize the model. So as a data, I used about 300 million lines of code, actually a bit more than that, from GitHub. And it took me about 2 hours to train it on 16 CPUs and 2 GPUs. So let me show you as a demo now. Since the demos, they always crash, so I will use YouTube. I hope YouTube will not crash. And here we go. Oh. Okay, so here now imagine that you are a software engineer that started on a new project, which is basically a web blogging platform, right? So you're just testing the platform, just trying to understand what's actually going on, and it's your first day. And one of the very intuitive tests will be just to create an article. And then you hit the bug, so the article is not being created. So what can you do really in order to understand what's going on and fix this bug? Well, there are a few things, right? So you can go to the repository, just go through all these files and try to read all the code and understand where really the article is created and where the bug could be. Another thing, you could go to the search bar and just type create article. It will not give you much, as you can imagine, because you have to know how exactly it's being named and whether there is even a method name or something like that. Or what you could do is you could try to run it on our engine that actually already have all the code in this project represented in the way that I described to you, and voila, we have exactly the point in code where the article is being initiated. So everything here you see is auto-generated using our model. So you see that there is a question, how to create a new article, which is describing what's happening there in the code. You have semantic tags, which create new article. Well, very good. That's pretty much what we're looking for. Related questions. So pretty much like Stack Overflow, it helps you just to navigate and to study the context a bit more. The architecture diagram is not finished yet, but the most interesting thing is that the function is actually called make article, not create article. And that's another the problem that very often is being faced, that you have to know exactly what the name has been used in order to identify. And this is the power of semantic search and basically the embeddings that are, in this case, mostly topological, in order to get the intelligence and bug fixes. Because you can imagine here, just within a couple of minutes, you were able to complete you were able to fix the bugs completely, right? Okay, so what we have seen is the following case. So this is the representation of pretty much all the variables and method names that has been seen in this project. And if we embedded them properly, so if we did choose the mathematical representation of everything that's happening inside the project, well, or here it's actually even across the different projects, then the entities that are very similar semantically, say different sorting algorithms or different features that are related to, in this case, creating an article. It could be also like a password generation or security measures and so on and so on. They will be close to each other, so we could cluster them together, and we will know that this actually means pretty much the same thing. So we can treat them as an entity of this similar semantics. Those that are dissimilar, they will be further apart from each other. And then you can just calculate the distance, whatever distance you like, correlation, cosine distance, anything. Although the accuracy here is quite good, but even the notion of accuracy for such problems, I think, is a very, very interesting task. Because if you read the literature, then you will face the very classic terms, which is a precision and recall, which are for NLP are called blue and rouge, and F1 score, which is basically a combination of blue and rouge. In our case, we calculated it for subtoken case insensitive, but it doesn't really matter. So, but when you deal with, and what is a precision and recall, basically? It's when, for a given piece of code, you are saying that this is about creation of new article. And then you check on how many of these labels the model will generate automatically. If it generates all three, then it's 1. If it doesn't generate everything, then it's 0. If there is overlap, then there is some percentage between 0 and 1. The problem is that we face a very interesting challenge with false positives and false negatives here, as different people might treat different tags as significant or insignificant differently. So basically, some people may say that for the example that you have seen, create article would be relevant, but new is not a relevant thing. So it will be different scores actually for different people. Especially when you go to a more complex examples, there will be a stratification also against the different roles. So that's why we are mainly calculating the relevance score, which is basically a satisfaction metric. It's how satisfied are the users with what we explain them is happening inside the code in natural language. And this is very tricky on how you can calculate it actually, because the relevance score and F1 are not directly correlated actually. So you can improve your models and you can see the improvement on all the classic metrics, but the users will not be very satisfied. So there are other problems with the unsupervised approach here. And one of them is that there is not enough depth. So as you have seen, the create and make, yes, we can catch it, which is very nice. But in this example, for example, look, there is this element which is called get available blocks, which actually is linked to this description, and this is from Stack Overflow, right? So this piece of code, this snippet of code was described as get free space on internal memory, and we will not be able to understand that actually get available blocks is exactly related to free space. So the depth is very limited for unsupervised approaches. Another problem is that we face infinite amount of degrees of freedom if we do not restrict our taxonomy. So labeling freedom should be based on a given taxonomy. And in Stack Overflow, you have seen it that you cannot just put any labels on your questions, for example. You have to follow their own taxonomy. So let me show you the second experiments that we did run. And in this case, we used pretty much the same libraries. For architecture, we did go a bit further because if before we were mostly looking at the tree structure and studying a topological, doing basically topological analysis of code, here we were also looking at the token and token level and a character level, and we were able to do that with combination of RNNs, CNNs, and LSTMs in this sense. Plus, we added the detention, and we have seen an amazing improvement in accuracy actually. So as you see here, we got on a test set almost 90%, or actually 88% here. And what is even more interesting that we got there within a few within a few if blocks. So what it really means actually in terms of understanding what's going on in code. So to such a question, what is security-related components? The unsupervised model didn't show any results really. And supervised one did show this as a relevant piece of code. To be fair, for me, it doesn't look as relevant to security one because I was not that familiar with JavaScript. But apparently, what it is doing, this line is restricting the session set cookies to be sent only when HTTPS is enabled, basically just by using HTTPS. And that's why it's being treated as a security one. So this kind of amazing things you can really do when you combine those and when you combine these different approaches and treat the code in such a manner. So the last cool results that I wanted to show you is basically this scatter plot graph that represents on how the different files, different snippets of code within one project are changed together. So our hypothesis was that if code is changed together within one commit, that it means that there is a certain semantics that is underlying this change, which means that you basically change these three different components, you're probably adding another button. So the next time you change these three components again, you're probably adding another button or something like that. So as you can see, most of the code actually has quite a lot of relationship and correlation between the changes, but there are some outliers, and the outliers sometimes show some amazing results. So this one, for example, have this name. Look at that. Do not use or you will be fired at React in Facebook component, and it's not been used with many others. So the same with very similar with other outliers. They're basically a representation of your tag depth and how the code is not being really very well incorporated or optimized in certain projects. So just from this topological analysis, actually, and very simple clustering here, but using the embeddings, you can see of what components actually have to be optimized and which components are in very good health. So basically, what I wanted to finish with is that these are the first results, but AI on code is coming, and it's a very, very interesting thing. I think there is a lot of treasure in data that is code, and some of the companies, such as Facebook, has some very interesting papers actually recently about the semantic search on their code too. Very company specific, but still. Google, obviously, Microsoft, and others, they're already doing it, and it changes the way and how they develop the code. And I'm absolutely confident that AI on code in general will change the way we are coding and developing software projects. So keep your eye on it. Thank you very much. Any questions?
You mentioned that your AI going to fix bugs, but most of prominent bugs come from not knowing or not understanding business logic behind the processes. Yeah. How can AI help here?
Yeah, that's a very good question. I didn't promise yet that we're going to fix your bugs completely. Don't misunderstand me. Exactly, actually, for this reason. So, as I said, the problem right now is with the depth of understanding and semantics of what is actually happening in the code. Right now, we're using with the classic or more advanced machine learning, and even sometimes deep learning, still help you to see the repeated code and study more of the patterns, basically to fix the bugs that have happened again and again and again and again. Those that are very company specific or very business specific or even happened for the first time, definitely not going to solve anytime soon. But that's the same actually with the generation of documentation. Or the code for that matter. I don't think that we will be able to completely replace software engineers or data scientists, that's for sure. But we can definitely take the most boring part of the job that has been repeated and duplicated so many times, and just free up your time and my time to do more exciting creative stuff, like fixing a business-related bugs here.
Just curious, does it work better with different languages or not, like statically typed languages or dynamic languages, or your model is agnostic to the programming language itself?
That's a very good question. So quick answer will be that this approach is language agnostic. But as you have seen from the diagram, you actually choose the level at which you want to. Basically, you should be always very task-driven. And if you're working just with one language, then you can much faster produce the model that will be very good with just one language. If you're more interested with working, say, with one specific task but across languages, you can just choose a different type of embedding, and that will be probably a strategy. So again, there is no silver bullet. Everything that I've shown here is a result of combination of models. So there is not even a single model that I can train and that will get me these results, really. And that's why there is need for this bit holistic approach that is then combined with a very task-driven specific one.
Anyone else? All right, thanks, Misha.
Thank you very much.
Thank you.